Hello. So what took you so long? Rupa B, Saujanya R, Hoysala B say, where were you? Hello? Hello, are you there? Hello, somebody answer me. Saujanya R, Rupa
Yes, sir.
B, are you there?
Sir, Supreet sir class ಇವಾಗ ಮುಗೀತು sir.
No problem. Fine. Yeah. So regarding the module 5, so like in the last class, we had seen basically the modeling of the resource allocation state of a system. And basically, we have here two kinds of models to be used. So one is the graph model, second one is the matrix model, so as to represent the state of a system. So this state of a system is nothing but this will convey the information regarding the resources that are being allocated to a process and the information about the pending resource request, so as to find so whether our system is in deadlock condition or not. So basically, we have two kinds of models to be used. So one is the graph model, second one is the matrix model. And in the last class, so we had seen RRAG. RRAG stands for resource request and allocation graph. So where we had the edges and the nodes. So the nodes will be represented as the process, like using a circle, like we'll be able to represent the process, and the resources are represented using the rectangles. And we had the edges as well. Okay. So we had discussed this RRAG. RRAG is basically one type of the graph model, so which comes under uh, the main graph model. So one is RRAG and second one was wait for graph. So in the last video, we had discussed this RRAG, resource request and allocation graph. Yeah, like this slide was been discussed. So where we have the representation of the processes involved in the system using circles, and I can represent the resource using the rectangle. And also these resource can be either a single instance or multiple instance. So we have something called as a resource class. An example given was a printer. So suppose if I take the say the bunch of 10 printers, so the bunch of 10 printers can be called as a resource class, and one individual printer in the bunch of printers can be called as a resource unit. Okay, so this resource can be a single unit, a single device, a single instance, or it can be multiple devices, multiple printers. Okay, right? And we also have this edges, like these arrow marks. So what you can see, so these arrow marks or edges can be like in two directions. Okay, so one is from the resource to the process, or the arrow mark can be from the process to the resource. And if the edge or the arrow mark is moving from the resource to the process, means it can be called as the sign edge. Similarly, if the arrow mark is pointing from the process and towards the resource, we call it as a request edge. Yeah, same thing has been shown here, nodes and edges, right? Yeah, so now coming to the second kind of the graph model, that is called as the weighted wait for graph model. Okay. Second kind of graph model is wait for graph model. And we have a simple example so as to know the concept of this wait for graph model. Okay, so you can compare this wait for graph model with the RRAG graph model, and we can have some understanding with respect to the wait for graph model. So this WFG, wait for graph model, is the next version or the enhanced version of RRAG, resource request and allocation graph, where we do not show the resources. Okay, like as you can see in the wait for graph model, so no resource is being shown in the graph model. Okay, like in case of this wait for graph, we do not show the resources, means resources will be made invisible. Okay, and if you see this RRAG means so we show the resources as well as the process. Okay, so but in case of this wait for graph, we don't show the resources, and resources will be made invisible. We just show the processes and their relationships. So you can see here that only the process P1, P2, and P3 are existing in the system along with their relationship. No resource is being shown in the waited for graph. So if you see this particular graph, okay, which is basically a RRAG graph model. Okay, so you can see here this P2 process is requesting for the resource R2. So you can see that by looking at the direction of the edge or the arrow mark here. So this process P2 is requesting for the resource R2. And this resource R2 is already been assigned to the process P1. Okay, and if you look at this particular arm, so where the process P3 is requesting for the resource R1, and this resource R1 is already assigned to the process P1. Okay, so here, so what you can observe here is, so both the process P3 here and P2 process are waiting for the process P1 to complete for their execution or completion. So here, same information where the process P3 and process P2 are waiting for the process P1 to complete. Same thing can be shown in this particular waited for graph. Okay, wait for graph where we are not showing the resources. Okay, so suppose if I delete this particular resource, okay, or if I'm not showing the resource R2 and R1 here means, so you can have an imaginary line which connects this process P2 with the process P1. And if I remove this R1 resource means I can have an imaginary line so which connects this process P3 with the process P1. And also you can make a note of the direction, right, of the edge or of the arrow mark. Okay, so this RRAG can be simply represented in terms of only the processes and their relationships using wait for graph. Okay, so this same diagram, what you're showing is being simply represented using the wait for graph, where these two process P3 and P2 process are waiting for the process P1 to complete. Okay, so to relate the diagram with respect to only processes, what we do is we simply remove the resources and connect the arrow marks as shown. Okay, right? And this will be called as the weighted for graph, where we are not showing the resources, right? Instead, we only represent the processes along with their relationships. Okay, yeah. So again, some more examples of this RRAG. So, but here the main point here is, so we have this multiple instance, or we have more than one number of resources. Okay, so in the resource class, okay, so you can expect more number of resources, right? Like as you can see here, the resource class R1 has got only one device or one instance or one resource. And in case of resource R2, right? Like in case of resource class R2, this has got two number of resources. Okay. Like this is a simple example of RRAG where we are having multiple instances. Okay. So for the resource class R2, this has got two number of resources. So where the dots will be indicating the number of resources. And as you can see here, so this resource R1 has got only one resource, and the resource class R2 has got two number of resources, and these two number of resources are being assigned for P2 and P3. Okay, so the resource class R1 contains only one resource unit. Here it is. Okay, and this resource unit of R1 is allocated to the process P1. Okay, and the process P2 and P3 are requesting for R1. Okay, so you can see here the direction of the edge. So these two process P2 and P3 both are requesting for the resource R1, so which has been already assigned to the process P1. So the units of resource class R2 are allocated to P2 and P3. See here. Okay, we have here two number of resource. Okay, so we have here two number of resource in the resource class R2, and both of them are allocated to the process P2 and P3. Okay, so one gets allocated to P2, and this resource gets allocated to the P3 process. Okay, a request for a request by the process P4 for one resource of R2 is still pending. See here. Okay, so the process P4 is requesting for the resource R2. Okay, and already we know that the resources of R2 means so one resource of R2 is been allocated to process P2, and second resource of R2 is allocated to the process P3. Hence, the request raised by the process P4 for one of the resource of R2 is still pending. Okay, so why? Because so both the resource units in the resource class R2 is already being allocated to P2 process and P3 process. Okay, so like this, you can have the analysis of the RRAG graph, where we are explaining the concept of multiple instances, multiple devices. Okay, so multiple resource units as such. Okay. So now we have some more examples on RRAG and WAG. So as you can see here, as we are representing the resource here, this can be called as a RRAG graph, and the same graph will be represented in terms of wait for graph, WFG. Okay. So the figure, like this one is showing, so we have here that, so you can find here three process, P1, P2, and P3 process along with a single resource, where P2 and P3 process are requesting for the resource R1. And this resource R1, single unit of resource R1 is already assigned to the process P1. Okay, so the same figure in RRAG can be shown in the WFG simply by removing this particular resource R1. Hence, we have the figure in this particular manner. Okay, so where P2 and P3 process are requesting for the process P1. So the edges P2, R1. Okay, here it is. Okay, so the edge P2, R1 and R1, P1, right? Like this flow, like indicated by the dotted line, can be replaced with the solid line from P2 to P1. Okay, so same thing they have done. So I should represent this RRAG graph in terms of wait for graph. Okay, similarly, the edge P3, P1, right, is indicating that the process P3 is waiting for the resource R1. Okay, and this R1 is currently allocated to the process P1. So the same thing is being represented using this edge in the wait for graph. Okay. So next is a very important concept. A deadlock cannot exist unless an RRAG or a wait for graph contains a cycle. So like if and only if say some set of process is able to have a loop, right, or a circle, so then we can say that the deadlock is existing. Okay, and if no loop, no circle is existing in a set of process, means the deadlock will not be existing. So according to this particular figure, like here I can find the existence of a loop or a circle. Okay, so by seeing the graph itself, you can tell that so whether deadlock is existing or not. So let me examine the graph. And if I'm able to start with the starting point Pi, means again we can come back for the same point Pi. Okay, transversing along the printer and the process PJ and one more resource tape, and again I can reach the same point. Okay, so there exists a circle or a loop, right, among these two process PI and PJ and these two resources, namely the printer and the tape. Okay, so if we see this particular edge means, okay, so the process PI is requesting for the printer. Like even though the process PI is assigned a resource called as the tape drive. Okay. So this process PI is requesting for the printer, even though it is holding the resource, the tape drive with it. And again, so like this edge indicates that the same printer requested by the PI is already been assigned to the process PJ. And apart from holding the resource, so-called printer by the process PJ, same process PJ is also requesting for the tape drive. Okay, so we have a sort of loop or a circular weight is been existing here. Okay, so we have a cyclic path here. Okay, so we have a loop here. Okay, so the starting point will be obviously the PI, where PI is requesting for the printer. This printer is assigned to PJ. This process PJ is requesting for the tape, and this tape is already held by the process PI. Okay, so this PI cannot access the printer as the printer is assigned to the PJ. Similarly, this process PJ cannot access the tape drive. Why? Because the tape drive is already been assigned to the process PI. So hence here, well, like I said, we have the existence of a deadlock. Why? Because here both the process PI and PJ process are waiting for each other to release the resources. Hence, here both the process PI and PJ are in a deadlock situation. So again, one more example for the multiple instances. Okay. And like I said, so by looking at the graph itself, you can observe that. So we have again circular weight is existing here. Why? Because so we have a loop here starting from the resource R1, and again I can reach the same point R1. Okay. So like this is so what we're discussing here is the resources can have the multiple resource units. Okay, so the resource class can have the multiple resource units. So where one resource of R2 is assigned to the process P2, and one more resource unit of R2 is assigned to process P3. Okay, so a cycle in an RRAG does not necessarily imply a deadlock. Okay, if the resource class has multiple resource unit, so very important statement. Okay, a cycle in an RRAG graph does not necessarily says that you do have a deadlock. Okay, like even though we have a circular weight here, like even though we have a loop here, and even though we have a cycle existing here, so but we cannot always say that there will be existing a deadlock. Why? Because like here we can find the multiple resource units, like as you can see here. So the resource class R2 is having two number of resources. Okay, so one is assigned to P2, and second resource of R2 is assigned to P3. Okay, yeah. So now let us examine this particular figure. So the resource R2 is a multiple instance. Why? Because so this resource class R2 has got here two number of resources, and you can see this. So this P3 is not requesting for any resource. Why? Because no edge is going from the from the P3 process to any other process or resource. Okay, hence this P3 is not requesting for any other resource, and P3 has already assigned with one resource of R2. Okay, so this P3 has already assigned with one resource of R2. So this P3 can be executed successfully. Why? Because whatever the resources that P3 is in need of, okay, already it has got the enough resources so that P3 can go for execution successfully. So once we have the execution of P3, Okay, so one resource of R2 will be freed. Why? Because upon the successful completion of any process, the resources that are allocated to the particular process will be released. Okay, so hence, after the successful execution of process P3, so one resource of R2 is freed. Okay, so this free resource of R2 will be assigned say to the process P1. Okay, so the P1 can also execute. Okay, so now when P1 gets executed, so then both the resource of R2, like this one and this one, both will be freed. Okay, hence the P2 process, which was requesting for one resource, can also get executed. Okay, so upon the execution of P3, so one resource gets freed, and as we have the requesting of P1 to the resource R2, so this free resource can be assigned to the P1, hence P1 can also get executed. Okay, and after execution of P1, the second process will also get executed, because so now both the resource will be free. Hence the P2, which was requesting for this R2 resource, can also execute. Okay, so hence we have the successful execution of all the process P1, P2, and P3. Okay. So now we'll see the next modeling of the resource request in a system, and that we call it as the matrix model. Okay, but as you can see here, so we have the use of various matrix. Okay, so we have the use of various matrices. Okay, so one we call it as allocated resource matrix, and second one is the requested resource matrix. Okay, and also we have some tables like say the free resource table, and also a table to indicate the total amount of resources available in system. Okay, so to explain this matrix model of this thing, so you can take the help of this particular figure. So we are again like we are dealing with the multiple instances. Okay, multiple resource units are there in the resource class. Okay, so the allocation state represented by the two matrices in case of a matrix model, right? So where the one matrix is allocated resources and second one is the requested resources, right? So if any system has got n number of processes and r number of resource classes, okay, as you can see here, so we have here the two resources. One is the printer and second one is the tape drive, right? And you can see here the use of two processes, PI and PJ. Okay, so if any system has got n number of resources and r number of resource class, each of these matrix is an n into r matrix. Okay, so according to this particular figure, so you can have the representation of the allocated resource matrix as well as the requested resource matrix. Okay, so how to draw this? Okay, so once we have the diagram given to you, okay, so once you have the RRAG given to you, so you can draw the allocated resource like in this way. Okay, so like in the column wise, so you can mention all the resources available. As you can see here, so we have here PI, I mean like, so we have here PI process and PJ process, as well as you do have PK process. Okay, like in this particular system, so we have so basically three process, PI, PJ, and PK process, and we have two resource class. Okay, so one is the printer class, which has got only one resource unit, and the resource class say by name tape drive has got two resource units. Okay, so on the column wise, you can write down all the processes present in the system, and those are PI process, PJ process, and PK process. And in the like and in the topper place, so you can write down the number of resources. So one is the resource printer, and second one is the tape. Okay, so you can form a table here, and so you can see the particular graph, and you can have the writing of the values, okay, or the numbers, right? Like with respect to the processes involved and how many resources of the printer and the tape are being allocated to each and every process, PI, PJ, and PK. So if you see the graph here, means so this particular one resource of tape drive is allocated to process PI, right? So you can write here 1. So for the process PI, so one resource of the resource class state is allocated to the process PI. Okay. And this PI process is not allocated to any printer. Okay. Means no printer is allocated to the process PI. Hence you can write here 0. Okay. Are we clear with the first row here? Hello? Are we clear with the first row? So by looking at the RRAG graph, you can enter these values. And if you see the second process PJ here, okay, so for the process PJ, you need to write down what all resources are being allocated to the process PJ. Okay, and if you look at this particular edge, means this indicates that so one resource of the printer is allocated to the process PJ. Hence, I can write here 1. Okay, and this particular PJ is not being allocated any tape resource. Okay, right? Hence, here you can write 0. Means no resource of tape is allocated to the process PJ. Hence, here I have written 0. And if you look at the third process PK, okay, so here, so one resource unit of resource class tape drive is allocated to process PJ, and that is shown by this particular edge. Hence, this particular process PJ has got one resource of the resource type called as tape. Okay, and this PK process is not being allocated any printer resource. Hence, I can write here 0. Okay, so are we done with this printer tape and the allocated resources of the printer and tape to these processes? Hence, the matrix called as allocated resources will be able to indicate so what all resources, right, in the system are being allocated to each and every process. Okay, so next kind of matrix is the requested resource matrix. So as the name itself indicates, requested resource matrix will be able to indicate the processes along with their requested resource. Okay, and if you see the same RRAG graph, means you can guess that so this particular process PI is requesting for which resource? Printer resource. Okay, hence here this process PI is requesting for the printer resource. Hence I can write here 1. And this process PI is not requesting for the tape resource. Hence here I can write 0. Okay, right? So in the top row, I can mention all the resource types, and in the column wise, I can write down all the processes available in the system, and I can go on filling the values here. And if we look at this second process PJ, so this PJ is requesting for the tape request. Okay, so this process PJ is requesting for the resource tape. Okay, so hence I can write here 1, and the same process PJ is not being requesting so for the printer. Okay, hence I can write here 0. Okay, and this process or the last process PK is not requesting for any kind of resource. Okay, hence here, so for the printer and for the tape drive, so you can enter the value of 0 here and one more 0 here. Why? Because this process PK, as you can see here, is not requesting for any resource as such. Okay, neither for the tape or for the printer. So this process PJ, this process PK is not requesting for any resource. Hence, I can write here 0, 0. And regarding this total resource, so like this structure will be indicating that what are all the available resources are there in the system. And as you can see here, so we have the printer, and the number of printers available in systems are only 1. Hence, I can write here 1. Along with that, you have the resource class, so by name tape, and this has got 2 number of instances, 2 number of devices, 2 number of resources are there. Hence, I can write here 2. And what about the free resources or the available resources. Okay. So just now, like we have seen the total amount of resources available in the system, and now we are seeing how many resources are free. Okay. And so for this table, like the values for printer and tape are 0, 0. Why they are 0, 0? Because even though we had one resource of printer, so but this one resource of the printer is allocated to the process PJ. Hence, this becomes 0. And even though we have here the two resource of tape drive, okay, so one gets allocated to process PI, second resource is allocated to process PK. Hence, this is also this is also 0, 0. Hence, no free resources are available in the system. Why? Because so one resource of printer is allocated to process PJ, and even though we have two resource units of the tape drive, so one gets allocated to the process PI, second gets allocated to the resource, like the process PK. So hence here, so both the resource of the tape drive are already been allocated to the process PI and process PK. Hence, no free resources are available in the system. Okay. So you can explain this matrix model so by taking this particular example and by using the allocated resource table and the allocated resource matrix and the requested resource matrix, you can represent the number of allocated resources to any process as well as the processes which are requesting for the resources. Okay. So next is so we have some problems. Okay. So we have some problems wherein you can solve or you can have some calculations to be done, and based upon the calculation, you can detect the existence of the deadlock. Okay. So by looking at the system also, you can gauge so whether we have the existence of deadlock or not. So, but this holds good only for simple systems. So, but for a larger system where you can find so many numerous number of processes and so many resources, let's say single instance, double instance, multiple instance. So it becomes much more difficult for us to look at the graph and tell whether the deadlock is existing or not. Okay, so for those kind of complex systems having many processes and many resources, okay, we do need to have some algorithm. Okay, so we need to have some algorithm so as to gauge that whether the deadlock is existing in the system or not. So that can be called as the deadlock detection algorithm. So we have an algorithm so as to have the detection of the deadlock. Okay, and algorithm is in this particular manner, and this particular algorithm can be better understood by seeing the simple example. Okay, so once you analyze the particular example, so then you can easily understand the steps involved in the algorithm. Okay, so we have here something called as matrix has been shown here, so where we have the allocation of the resources as well as the request of the resources. Okay, the request for the resources raised by these three processes. So you can simply observe this particular this particular RRAG, okay, resource request and allocation graphic. You can see this where we have here how many processes are there? P1, P2, and P3 processes are there. Hence, you can write down all the processes in the column wise. Okay, and at the topmost rows, you can find the allocation matrix as well as the resource request matrix. Okay, so in the figure, so we have here how many resources? Only two resources are there, R1 and R2. Okay, hence you can write down the resources in second row. Okay, R1 and R2 are the two resources, okay, available, right? So now, so like how to fill these values. So first, let me look at this allocation of the resources for these three processes, P1, P2, P3. So let me start with the first row, where we are dealing with the process P1. Okay, so you can look at the figure and fill the allocation of request matrix for the process P1, P2, and P3. So if you look at the figure, means, so here this resource R1 is allocated to the process P1. Okay. Okay. So this resource R1, so this single resource of R1 is allocated to the process P1, right? So hence you have written here 1. Okay. So this resource of R1 is already allocated to the process P1. Hence here I can write 1. And if you look at the figure like regarding R2, so this R2 resource is not allocated to the process P1. But because no arrow is pointing from the resource R2 to the process P1, hence this becomes 0. And if you look at the second process P2 means, so what all resources are being allocated to the process P2, as you can see here, so one resource of R2 is allocated to the process P2, and that has been shown using this particular edge. Hence here, and the same information is being entered in the table. So resource R2 is allocated to the process P2, hence here I can write 1. And no resource of R1 is allocated to the process P2. Hence, you can write here 0. But because no arrow mark is going from the resource R1 to the process P2, hence here I can enter 0. And if you look at the third process, okay, so this third process, like this third process is not being allocated with any resource, right? Either R1 or R2. No resource is being allocated to the process P3. Why? Because no arrow mark is pointing from these resource and towards the process P3. Hence, this process P3 is not requesting for any resource. Hence, these two values becomes 0 and 0. Okay. Now going for the request, like resource request matrix. Okay. So how to enter this? Again, we have here the same three processes, P1, P2, P3. And I can find two resources, R1 and R2. Okay, the same thing is being written here. So now we are seeing the resource request. Okay, right? Resource request raised by these processes for these two resources. Okay, so again, you can see the diagram. Okay, so with respect to the process P1, right? So the resource request for resource R1, is it there? So this process is not requesting for resource R1, okay, nor R2. Hence, these two become 0, 0. And if you look at the second process P2, so this P2 is also not requesting for either the resource R1, okay, nor the resource R2. Why? Because no arrow mark is leaving the process P2 and moving towards R1 or R2. Hence, this process P2 is not requesting for either resource R1 or R2. Hence, this value becomes 0, 0. Now we can look at the third process. Okay, so this third process P3 is requesting for the R1 resource as well as R2. Why? Because we have two arrow marks leaving the process P3 and they are pointing towards R1 and R2. Hence, the third process P3 is requesting for the resource R1 as well as R2. Hence, I can write here 1 and 1. Okay. Now, we need to enter one more table called as the availability of resources. Okay. So, what we have seen here. So, what we have seen here, the free resources or the number of resources that are rightly free here. Okay, so that needs to be entered. Okay, so the availability of resources by seeing this particular RRAG graph is written here. So basically, you can find here how many resources? Two resources, R1 and R2. Okay, and what about the availability of resources? Even though we have two resources, so one resource of R1 and one more resource of R2, but this resource R1 is already been assigned to process P1 and this resource R2 is already been assigned to second process P2. Hence, we don't have any resources left or the number of free resources left is 0, 0. This indicates what? We have 0 resource of R1 and we have 0 resource of R2. Are you there? Anybody? Answer me. Anybody there? Are you listening?
Yes, sir.
So we have no free resources available in the system because both the resources R1 and R2 are being allocated to the process P1 and P2. Hence here we have zero resource of R1 and zero resource of R2. So by having the 0, 0 resource of R1 and R2, can we satisfy any of the request raised by the process P1, P2, and P3? Okay, so this process P1